4 watts a year. That's the number nobody talks about, and it's the number that explains everything that's about to unfold in this story. 4 watts, lost every single year, slowly bleeding out of a machine that has been flying through the dark for almost 50 years. That's it. That's the quiet, unglamorous countdown clock that's been ticking since before most of the people watching this were even born. And on February 27th of this year, that countdown clock did something engineers had been dreading for a very long time. During a routine roll maneuver, a simple rotation the spacecraft has performed thousands of times without incident, Voyager 1 experienced an unexpected and unexplained drop in power. Not a dramatic explosion, not a catastrophic failure. Just a quiet electrical stumble 15 billion miles from home that came dangerously close to triggering the one system on board nobody wants to see activate. The undervoltage fault protection routine, a last resort safeguard that automatically starts shutting things down when the spacecraft senses it's running critically low on power. Voyager 1 turned, and for a moment it looked like it might not turn back the same way it went in, and that single quiet moment out in interstellar space confirms something scientists have known was coming for years, but have been almost afraid to say out loud in plain terms. This mission is dying, on a schedule we can now actually calculate, and the end is no longer some abstract decade off in the distance. It's close enough to count. Let's back up and understand exactly what we're talking about here, because the scale of this thing is almost impossible to hold in your head properly. Voyager 1 launched in September of 1977, originally built for a mission that was only ever supposed to last about 4 years, a quick tour past Jupiter and Saturn before the engineers figured its job was basically done. Nobody in that control room in the late 70s seriously expected this spacecraft to still be transmitting data back to Earth in the year 2026. And yet here it is, nearly 50 years later, still the single farthest human-made object ever built, still pushing outward at roughly 38,000 miles per hour, currently sitting somewhere around 15.8 billion miles from Earth. It crossed the heliopause back in 2012, the invisible boundary where the sun's magnetic influence finally gives way to true interstellar space. Becoming the first spacecraft in human history to physically leave the bubble, our star has been blowing around our solar system for billions of years. In November of this year, it's set to cross another milestone entirely, becoming the first human-made object to sit a full light day away from Earth, a distance so vast that a radio command sent up on a Monday morning wouldn't even arrive until Wednesday, and any reply wouldn't get back to mission control until Thursday. That's not science fiction. That's the actual operational reality NASA's own Voyager team is currently working inside of, and it's the exact kind of scale that makes this story worth sitting with for a minute. Because a machine built with 1970s technology is still functioning, still thinking, still measuring the universe at a distance almost nothing else humanity has ever built could survive reaching. But here's the part that doesn't get nearly enough attention, because the headlines love to celebrate the distance milestones while quietly burying the story underneath it. Voyager 1 isn't powered by sunlight. Out here, this far from the sun, solar panels would be functionally useless. So both Voyager spacecraft rely instead on radioisotope thermoelectric generators, compact devices that convert heat from slowly decaying plutonium into usable electricity. When Voyager 1 launched, those generators were producing somewhere around 470 watts of power, enough to run a full suite of 10 scientific instruments along with cameras, heaters, and every other system required to keep the spacecraft alive and functioning. Today, after nearly 5 decades of steady radioactive decay, that output has fallen to somewhere in the neighborhood of 230 to 250 watts, roughly half of what it started with, and it keeps dropping by that same relentless 4 watts every single year, with no way to reverse it, no way to refuel it, and no way to send a repair crew 15 billion miles to swap out the batteries. This isn't a malfunction. Nothing broke. There's no glitch to patch, no software bug to squash. This is simple, unforgiving physics, a nuclear power source quietly running down exactly the way physics always said it eventually would. And the entire mission has now become a decades-long balancing act between keeping the spacecraft warm enough to survive and keeping enough instruments alive to still call it a functioning scientific mission. That balancing act has forced some brutal decisions over the years, and if you look at what's actually been switched off, you start to see the real shape of this decline far more clearly than any single dramatic headline could show you. The cameras that once captured those legendary portraits of Jupiter and Saturn were shut down decades ago once their primary mission wrapped up. The plasma science instrument was powered down after its performance degraded past the point of being useful. The ultraviolet spectrometer outlived its original planetary assignment by decades before it, too, finally got the shutdown command. Then, in February of 2025, engineers pulled the plug on the cosmic ray subsystem specifically to conserve power. And then, on April 17th of this year, mission controllers sent the command that turned off the low-energy charged particles experiment. an instrument that had operated almost continuously since the moment the spacecraft left Earth, measuring ions, electrons, and cosmic rays streaming in from both our own solar system and the wider galaxy beyond it. That single instrument had spent nearly 49 years helping scientists understand the actual structure of interstellar space itself, detecting pressure fronts and shifting particle densities in a region no other spacecraft in human history has ever directly sampled. Losing it wasn't just another item crossed off a maintenance checklist. It was the loss of one of only 2 remaining scientific eyes this spacecraft had left on the universe around it. There's also a human dimension to this story that's easy to overlook when you're focused purely on watts and instrument tables. The scientists who originally designed some of these instruments back in the 1970s are, at this point, either retired, elderly, or in some cases have already passed away, which means the responsibility of nursing this spacecraft along has effectively been handed down across multiple generations of engineers, many of whom weren't even born when Voyager 1 first left Earth. That handoff itself is a remarkable achievement in institutional memory. A decades-long relay race where each new team has to learn the quirks of a computer system built on technology that predates the personal computer, the internet, and even the pocket calculator as most people know it today, all in order to keep asking a machine from another era to squeeze out just a little more science before it finally goes quiet. Every command sequence sent up to Voyager 1 today has to account for programming decisions made by engineers who assumed, reasonably, that nobody would still be operating this hardware anywhere close to 50 years later. That the current team can still coax meaningful science out of a computer with a fraction of the processing power of a modern wristwatch says as much about human ingenuity and patience as it does about the spacecraft's own remarkable durability. Which brings us to where things stand right now, in the summer of 2026. Voyager 1 currently has exactly 2 functioning science instruments remaining on board: a magnetometer, which measures the magnetic fields threading through interstellar space, and a plasma wave subsystem, which listens for the faint electromagnetic signatures rippling through the thin plasma that fills the space between stars. That's it. Out of the original 10 instruments this spacecraft carried into space nearly 50 years ago, only 2 are still switched on, still listening, still translating the emptiness of interstellar space into numbers a team back on Earth can actually study. And engineers are now openly discussing a timeline where even those final 2 instruments eventually go dark sometime in the 2030s, at which point the spacecraft would likely still be alive in an engineering sense, still capable of transmitting a basic signal home, but effectively finished as an active scientific mission. The measuring would stop. The listening would stop. What would remain is simply a very old, very distant, very quiet machine, still drifting outward, still carrying its message to the stars, but no longer telling us anything new about the universe it's passing through. So let's talk about the fix engineers have been racing to implement, because this is where the story gets genuinely tense, and it's also where that February power scare fits directly into the bigger picture. The team at the Jet Propulsion Laboratory has been developing a maneuver they've internally nicknamed the Big Bang, and despite the dramatic name, the concept underneath it is actually fairly elegant. The idea is to swap out a whole group of powered devices on the spacecraft all at once, turning off several higher power components, like the heaters currently keeping the thruster fuel lines from freezing solid in the near absolute zero temperatures of interstellar space, and replacing them with lower power alternatives that do the same essential job while drawing significantly less electricity. If it works cleanly, the maneuver could free up enough power to delay the next instrument shutdown by roughly a full year, and in a best-case scenario, it might even allow engineers to reactivate the low-energy charged particles instrument that was switched off back in April, giving that piece of the mission a genuine second life. NASA deliberately chose to test this maneuver on Voyager 2 first, since that spacecraft currently has slightly more power in reserve and sits somewhat closer to Earth, making it the safer of the 2 probes to experiment on. Those tests were scheduled to run through May and June of this year, and assuming they went well, the plan was always to attempt the same maneuver on Voyager 1 no earlier than July, which puts this exact moment right now squarely inside the riskiest phase of the entire plan. Here's why that timing matters so much, and why that February power stumble should be sitting uncomfortably in the back of your mind through all of this. Sending a single command to Voyager 1 currently takes over 22 hours to arrive, and confirmation that the command actually worked takes another 22 hours to travel back. That means every single decision involved in this maneuver unfolds across a communication gap of nearly 2 full days, with absolutely no ability for engineers to intervene in real time if something goes sideways in the middle of it. When that unexpected power drop occurred back in February during a completely routine roll maneuver, one the spacecraft had executed without incident more times than anyone could easily count, it demonstrated exactly how thin the margin for error has become. This is a machine so close to its electrical limits that a maneuver it has performed flawlessly for decades can now, without warning, tip it toward a fault protection routine that exists specifically to start shutting things down automatically in order to keep the spacecraft from losing power entirely. Reversing something like that, from 15 billion miles away, with a 2-day round-trip communication delay standing between every command and its confirmation, is about as close to performing surgery blindfolded through a mail slot as modern engineering ever gets. Think about what that 2-day round-trip communication delay actually means in practical terms, because it's easy to say the number out loud without really absorbing what it means for the people doing this job. Imagine trying to perform a delicate piece of surgery where every single instruction you give has to be written down, mailed across an ocean, and acted on by someone else entirely, with no ability to see what's happening in between, and no way to course correct until a full 2 days have passed. That's essentially what commanding Voyager 1 has become. Engineers don't get to watch a live readout and adjust in real time the way you'd expect from mission control in a movie. They send a carefully tested sequence of commands, and then they wait, for the better part of 2 days, hoping the spacecraft interprets everything correctly, executes it cleanly, and doesn't trip some internal safeguard along the way that could cascade into a bigger problem before anyone on Earth even knows there's an issue unfolding. The February power scare is a perfect example of exactly that dynamic. Nobody watched it happen as it happened. Engineers only learned about the drop after the fact, once the data finally made its long crawl back across billions of miles of empty space, by which point the actual event was already almost a full day and a half in the past. Now here's the honesty check, because it's important not to swing too hard into pure doom about all of this. Voyager 1 is degraded. Voyager 1 is not gone. Even stripped down to just 2 working instruments, this spacecraft is still delivering something genuinely irreplaceable to human science, because it remains one of only 2 machines ever built that can directly sample the environment beyond our solar system's protective bubble. Back in 2020, before some of these more recent shutdowns, Voyager 1's magnetometer picked up a sudden jump in the intensity of the magnetic fields embedded in the thin plasma surrounding it, while its plasma instrument simultaneously registered a corresponding rise in plasma density. Researchers eventually pieced together what was happening. Powerful bursts of plasma erupting from the sun were slamming into the outer boundary of the heliosphere, sending pressure waves rippling outward that compressed the interstellar plasma and intensified its magnetic field, essentially acting like a piston pushing outward from our own solar system and physically reshaping the space around a spacecraft that had already crossed the border years earlier. That's not something any telescope on Earth, no matter how powerful, could ever observe directly. That data only exists because a 50-year-old machine happened to be sitting in exactly the right patch of interstellar darkness, with exactly the right instruments still running to catch it. Every additional year the spacecraft survives is another year of data that literally cannot be collected any other way, by any other mission currently flying or even currently being planned. Before we go further into what's coming next, it's worth actually appreciating what this spacecraft accomplished to earn the right to be the subject of a story like this one in the first place, because Voyager 1's resume is almost absurd by modern standards. It launched on September 5th, 1977, 16 days after its twin, Voyager 2, on a faster, more direct trajectory that let it reach Jupiter first in 1979, followed by Saturn in 1980. Along the way, engineers actually faced a real choice about where to send it next. Continue on toward Pluto, or divert past Saturn's largest moon, Titan, to study its unusually thick atmosphere. They chose Titan, a decision that effectively ended any chance of a Pluto flyby for this particular spacecraft, but delivered groundbreaking data about one of the strangest moons in the solar system. Along the way, Voyager 1 handed back the first detailed close-up images humanity had ever seen of Jupiter's swirling storms and Saturn's intricate rings, images that reshaped textbooks and, honestly, reshaped how an entire generation of scientists and engineers imagined the outer solar system for the very first time. And strapped to the outside of the spacecraft the whole time was the Golden Record, a gold-plated copper disc loaded with images, natural sounds, spoken greetings in dozens of languages, and a curated selection of music from across human history and culture. A genuinely poetic, slightly optimistic bet that someday, somehow, something or someone out there might find it and understand it was meant as an introduction. That original mission was budgeted for roughly 4 or 5 years. It has now run for nearly 50. And that scarcity is really the heart of why this story matters so much more than a simple obituary for an old spacecraft. There is no backup Voyager waiting in a hangar somewhere. There's no quick replacement mission that could be launched tomorrow and reach interstellar space in any time frame shorter than several decades, even using the fastest propulsion technology humanity currently has access to. Voyager 2, Voyager 1's twin, is still out there as well, trailing not too far behind in relative cosmic terms, currently about 2 billion miles closer to Earth and moving somewhat slower, which means it will never catch up to its sibling no matter how much time passes, since the 2 probes aren't even headed in the same direction anymore. Voyager 2 is, for the moment, in a slightly better position, still running 3 functioning science instruments compared to Voyager 1's 2, giving that mission a bit more breathing room before it faces the exact same reckoning its twin is facing right now. But it is facing the exact same underlying physics, the exact same slow 4-watt per year bleed, and the exact same eventual date with silence somewhere down the line. Both spacecraft are, in the most literal sense possible, running out the clock together, just on slightly different timers. Voyager 2's own journey has actually been the more scenic of the two, in a manner of speaking, since it took what's often called the Grand Tour route, becoming the only spacecraft in history to fly past all 4 of the solar system's gas and ice giants, visiting Jupiter, Saturn, Uranus, and Neptune in sequence before it, too, eventually pushed out into interstellar space. That longer, more circuitous path is part of why it's trailing Voyager 1 in raw distance today, even though it actually launched 16 days earlier. The two spacecraft aren't just behind or ahead of each other on the same road either. They left our solar system heading in genuinely different directions, sampling different regions of the boundary between our sun's influence and true interstellar space, which is exactly why losing either one individually would mean losing an entire irreplaceable perspective, not just a redundant copy of the other. And here's the part that should genuinely worry anyone who cares about keeping a continuous human presence out in that region of space. There is currently no spacecraft flying, under construction, or even fully funded, that is designed to pick up where Voyager 1 eventually leaves off. There is a concept seriously studied by engineers at Johns Hopkins University's Applied Physics Laboratory called simply Interstellar Probe, designed from the ground up to be humanity's first spacecraft, built specifically for interstellar science, rather than one that stumbled into the job after finishing a planetary tour, the way both Voyagers did almost by accident. On paper, it's a genuinely exciting design, meant to launch sometime in the 2030s, travel roughly twice as fast as Voyager 1, and reach the heliopause in a fraction of the time it took its predecessor, potentially covering hundreds of astronomical units within its operational lifetime. But that's the key word: concept. It remains a proposal, dependent on future budget decisions, future launch vehicles, and a level of long-term institutional commitment that spans not just years, but potentially multiple generations of scientists and engineers who will need to hand the project down to their successors, the same way Voyager's original team has been doing for decades now. Even in the most optimistic timeline where funding materializes and a launch actually happens on schedule, there would still be a real gap, potentially a decade or more, where humanity has no active spacecraft directly sampling the environment beyond our solar system at all. Voyager 1 isn't just fading. In a very real sense, it might currently be irreplaceable on any timeline shorter than a full career. It's worth sitting with what actually happens when that clock finally runs out, because it's not the dramatic ending people sometimes imagine. There's no explosion, no final burst of static, no dramatic last transmission. The most likely outcome, based on everything engineers currently understand about how these spacecraft are aging, is a quiet transition. At some point in the 2030s, if the spacecraft survives that long, the shrinking power margin will eventually reach a point where even the final remaining science instrument can no longer be kept powered and warm at the same time. At that stage, the mission's scientific chapter effectively closes. The spacecraft may still be capable of sending back a basic engineering signal for some additional stretch of time after that, a kind of faint heartbeat confirming it's still out there, still functioning on the most basic level, even after it's stopped teaching us anything new about the universe around it. Eventually, even that heartbeat fades, not because anything catastrophically fails, but simply because there won't be enough electricity left to power the transmitter strong enough to reach a receiver 15, 16, 17 billion miles away. After that, Voyager 1 doesn't stop. It keeps moving silently forever, carrying its golden record with its greetings and its music and its sounds of Earth, drifting through the space between stars, long after every person who ever worked on this mission, and probably every person watching this right now, is gone. That's genuinely a strange thing to sit with for a moment. Long after the last engineer who understands this spacecraft's original systems has passed away, long after the Deep Space Network dishes that currently track it have been replaced or decommissioned, long after anyone on Earth is still listening for its signal at all, Voyager 1 keeps going, carrying that same gold record, still theoretically playable by anything with the right kind of stylus and the patience to follow the etched instructions on its cover. It becomes less a functioning spacecraft at that point and more a kind of message in a bottle. Except the ocean, it's drifting across measures in light years instead of miles, and there's a real chance nothing will ever find it, ever, in the entire remaining history of the universe. That's not meant to be depressing so much as genuinely humbling. Humanity built something durable enough to outlast its own builders, outlast the civilization that created it, and very possibly outlast the sun itself, all while running on less power than a typical refrigerator light bulb. And that ties directly back into why the milestone coming up this November carries so much extra weight this particular year. When Voyager 1 crosses that one light day threshold on November 18th, it won't just be a nice round number for headline writers to celebrate. It will be humanity watching its most distant emissary reach a distance where even the fastest form of communication physically possible, a beam of light itself, takes a full day just to make the trip one direction. Coming just a few months after a power scare that nearly triggered an automatic shutdown and right in the middle of the riskiest software and power reconfiguration this mission has ever attempted, that milestone lands less like a celebration and more like a checkpoint. A moment to pause and recognize just how far this spacecraft has traveled, while simultaneously acknowledging how much closer it's crept toward the edge of what its aging power supply can actually sustain. Reaching one light day away and running out of usable power within the same calendar year isn't a coincidence worth ignoring. It's the same slow, patient physics, playing out on two different fronts at once, distance climbing while power falls, two curves on the same graph finally starting to cross. So what does this all actually confirm? The thing everyone watching missions like this has quietly feared for years without wanting to say it plainly. It confirms that the golden era of direct human contact with interstellar space has a visible, calculable expiration date now instead of a vague, comfortable someday. It confirms that the handful of scientists who have spent entire careers working with Voyager data are now operating on borrowed time, watching a finite and shrinking window rather than an open-ended one. And it confirms something a little more uncomfortable to sit with too, which is just how thin the line has become between this mission continuing to make history and this mission simply stopping. Quietly, during an otherwise routine operation, the same way it nearly did back in February. Every command sent to this spacecraft from this point forward carries just a little more weight than the one before it, because nobody actually knows which one might turn out to be among the last that gets answered. Step back far enough, and the bigger picture here isn't really about one aging spacecraft at all. It's about how narrow humanity's window into interstellar space actually is right now, and how easily that window could close for a while before anyone manages to reopen it. Every telescope on or around Earth, no matter how sophisticated, is still observing interstellar space from a distance, filtered through the same solar wind and heliospheric boundary that Voyager 1 physically crossed back in 2012. Only a spacecraft that has actually punched through that boundary can tell scientists what the plasma density, magnetic field strength, and particle composition genuinely look like on the other side, in real time, without having to infer it secondhand. Lose that direct sampling capability, even temporarily, and an entire field of research effectively goes dark until a successor mission, whenever it eventually launches, spends its own additional decade or more crossing the same boundary all over again. That's the quiet stake sitting underneath every watt of power this team manages to squeeze out of a nearly 50-year-old nuclear battery. It's not just about keeping a historic spacecraft alive for sentimental reasons. It's about keeping a single, irreplaceable scientific vantage point open for as long as physics will possibly allow. There is still reason for genuine optimism buried in all of this, and it's worth ending on that note rather than pure gloom, because the story isn't finished yet. If the Big Bang power maneuver succeeds on Voyager 1 the way engineers hope it will, the spacecraft could realistically keep transmitting real, usable science well past its 50th anniversary in 2027, possibly even long enough to see that low-energy charged particles instrument switched back on and contributing fresh interstellar data once again. The team behind this mission has, time and time again over the better part of 5 decades, found creative ways to squeeze a little more life out of a machine that was never designed to survive this long in the first place, coaxing extra years out of dwindling power reserves through nothing but careful engineering, patience, and a willingness to make hard trade-offs 1 watt at a time. That track record is genuinely remarkable, and it's the exact reason this spacecraft is still flying, still listening, and still teaching us things about the universe nearly half a century after everyone assumed its job was already done. But track records, no matter how impressive, don't change the underlying physics driving all of this. The plutonium keeps decaying whether the maneuver works or not. The 4 watts keep disappearing every single year, on schedule, indifferent to how badly anyone wants this mission to keep going. And somewhere out past the edge of our solar system's magnetic influence, 15 billion miles from every person who will ever read about this story, a 50-year-old spacecraft that once showed humanity its first close-up look at Jupiter and Saturn is now quietly, steadily running out the very last of its power. 1 watt, 1 command, 1 nervous round-trip signal at a time. There's something almost poetic about the fact that the moment which finally confirmed everyone's quiet fears wasn't some dramatic collision or catastrophic failure, but a routine roll, the kind of maneuver this spacecraft has performed without a second thought thousands of times since the disco era. It wasn't a meteor strike or a solar flare or some external threat reaching out from the void to silence humanity's furthest voice. It was simply time, doing what time always eventually does to anything built with a finite power source and an infinite journey ahead of it. That's a strange kind of ending to prepare for. Not sudden, not violent, just patient and mathematical, arriving exactly on the schedule the physics always promised it would, whether anyone back on Earth was ready to hear it or not. What do you think happens first? Does the Big Bang maneuver actually buy this mission the extra years engineers are hoping for? Or are we watching the beginning of the real final countdown play out in real time? Do you think Voyager 1 makes it to its 50th anniversary next year still collecting genuine science? Or does the next power scare turn out to be the one that finally forces the last instrument dark for good? Let me know what you think down in the comments, because there are a lot of strong opinions on both sides of this one, and it's worth hearing where people actually land. If this kind of deep dive into what's really happening out at the edge of human exploration is the kind of thing you want more of, go ahead and like this video, share it with someone who'd find this as fascinating as you clearly do, and subscribe so you don't miss the next update the moment new data comes back from 15 billion miles away. Because whatever happens next with this spacecraft, it's going to be worth watching closely. Thanks for watching, and we'll see you in the next one.